To name molecular compounds, the rules say that you name the first element in the formula, then you name the second element in the formula, but you drop the ending to the name of the second element, dropping that ending and replacing it with IDE. And then finally, you use Greek prefixes in front of each name in order to denote how many of those types of atoms are in the formula of the compound. However, if for the first element there's only one of those types of atoms in the formula, then you do not use the Greek prefix mono. And so the Greek prefixes that are used are shown here on the side. So for the first compound, N2O5, N is the symbol for nitrogen. O is the symbol for oxygen. We drop the ending of the second element and replace with IDE. And the second element, there are 5 oxygens. The second element is oxygen, and there are 5 of them. So that would be penta. The first element, there are 2 of them. There are 2 nitrogens, the first element in the formula. So we use the prefix di. So the name of this compound is dinitrogen pentaoxide. Another thing that you'll see in most chemistry textbooks, if the Greek prefix ends in A, like tetra, penta, hexa, hepta, octa, and the element is oxygen, then you can drop the A. So you can call it pentaoxide or pentoxide. Either one is considered correct. SO3, S is sulfur, O is oxygen, but we drop the ending and replace with IDE. There's only one sulfur. If there's no subscript, then it's understood to be 1. So there's only one sulfur, and sulfur is the first type of atom in the formula. So we don't need to use the Greek prefix mono for the first element when there's only one of them in the formula. And then finally, the second element, oxygen, there are 3. So we use the prefix tri. SO2 then would be sulfur dioxide. CO2 would be carbon dioxide. Again, there's only one sulfur in SO2, only one carbon in CO2. And so therefore, we don't use a Greek prefix for the first element when there's only one of the first element in the formula of the compound. CO, there's one carbon, there's one oxygen. So again, there's only one carbon, and carbon is the first element in the formula. So we don't use the Greek prefix mono. We just use the name of that element, carbon. And then there's only one oxygen, but oxygen is the second element in the formula. So for the second element, if there's only one, you do use the Greek prefix mono to indicate one. So CO is carbon monoxide. P4O10. P is phosphorus. And then you got 10 oxygen, so oxygen oxide. The prefix for 10 is deca. And so again, I dropped my A on my prefix deca and just called it decoxide. So phosphorus decoxide, but there's 4 of the first element, phosphorus. So I put the prefix tetra. Tetraphosphorus decoxide. If CO is carbon monoxide, NO is nitrogen monoxide. If CO2 is carbon dioxide, NO2 is nitrogen dioxide. CCl4, C is carbon, and there's only one of them in the formula, so I don't use the Greek prefix mono in front of the carbon. So it'll just be carbon. And Cl is chlorine. I dropped the ending and replace it with IDE, so that's chloride. And there are 4 chlorines in the formula, so that would be tetra chloride. So carbon tetrachloride. And PCl3 with 3 carbons, that's going to be trichloride. And there's only 1 phosphorus in the formula, so that would just be phosphorus trichloride. The next set of questions deal with concentration units, percent, ppm. And so if the concentration of argon in the air is 0.934%, that means you got 0.934 parts per 100. Convert this to parts per million. And so the fraction or conversion factor that you need to convert between parts per 100, which is percent, so if I'm converting from parts per million to percent or parts per 100, I would use this form of the conversion factor. However, in question 1, we're converting a percent or parts per 100 to a parts per million, so we would use this form of the conversion factor for question 1. So 0.934 parts per 100. We multiply that by this conversion factor. The parts per 100 cancel. We've got it set up correctly. Now we just need to do the math. And again, if you're doing calculations with exponents and you're not getting the correct answer, the problem could be you're not putting your exponents in your calculator correctly. I posted a set of math review videos And of those videos, there's one on how to use a scientific calculator. So I heavily advise you to take a look at that video on using a scientific calculator if you're not completely confident and sure that you are putting in exponents correctly. Because back in the good old days, seems like forever ago, when we were actually having on-ground classes, each semester I noticed there would be a few students that were working problems in class and they're like, I'm just not getting the same answer as you. I don't know what I'm doing wrong. And the problem was they weren't putting their exponential expressions in their calculator correctly. And that's why they couldn't get the correct answer. They were setting the problems up perfectly, but they were just inputting their numbers in their calculator wrong. And so definitely check out that video to make sure that you're confident in using your scientific calculator. So we'll take 0.934, multiply by 1 times 10 to the 6. And so if this setup doesn't make you feel comfortable, I always tell students that are in the beginning stages of learning and feeling comfortable doing unit conversions and dimensional analysis, put that first number as a fraction and put 1 as the denominator. You didn't change the number, but now both expressions look like fractions. And so the rule, remember way back when in middle school, you learn how to multiply and divide fractions. To multiply fractions, you multiply all numerators by each other, multiply the denominators by each other, and then the final step is do the division, okay? So you multiply 0.934 times 1 times 10 to the 6. You get that result. And then you divide because the first number, the first denominator is just a 1. So 1 times that number, of course, is still that number. So you take that product and just simply divide it by 1 times 10 to the second, and you get 9.34 times 10 to the third parts per million. For number 2, we're doing the opposite. So for question number 2, we're going to need this form of the conversion factor. We're converting parts per million to percent or parts per hundred. And so a smoker exhales 20 to 50 parts per million carbon monoxide. Express this concentration range as a percent. So 20 to 50 parts per million is equal to how many parts per hundred? So first we take 20 parts per million and we convert it to parts per hundred. So we get 2 times 10 to the negative third pph, which is the same thing as 2 times 10 to the negative third percent. And then the higher end of the range, 50 parts per million, and so therefore the range of carbon monoxide that a smoker exhales expressed as a percent, so if we change our exponential expressions to long form, so that range of carbon monoxide in a smoker's exhaled breath is going to be 0.02 to 0.005%. And all I did here was something that you learned way back when in elementary school. I just converted the number from scientific notation into regular form, which we call long form. Scientific notation is like a shorthand form. And so basically all I did was take the number 2, put some zeros in the front, move the decimal 3 spaces to the left. A non-smoker only exhales 0 to 2 parts per million of carbon monoxide. Express this range as a percent. So 0 parts per million is going to be 0%. But what is 2 parts per million converted into a percent? We do the same type of calculation we did in question 2, using the same conversion factor. And then again, I take 2 times 10 to the negative 4, and I'm going to convert it from scientific notation to long form and move that decimal 4 spaces to the left. So 0.0002%. So the range of carbon monoxide that's exhaled by a non-smoker is 0% to 0.0002% carbon monoxide. On a humid day, water vapor concentration in the air is 8,500 parts per million. Convert this to a percent. We're going to, again, use the same conversion factor that we used in problems 2 and 3. The parts per million canceled. You get 0.85 parts per 100. Which is the same as 0.85%. Question 5. If you had a sample of 500 particles of air, how many of these particles will be oxygen? How many will be nitrogen? How many will be argon? Well, air is 21% oxygen, 78% nitrogen, and about 0.9% argon. So if you have 500 total particles, you take these percentages, convert them to a decimal, something we learned to do again way back when in elementary to middle school. You just take the decimal, and with these big numbers that don't have a decimal, you place the decimal at the end, and then just move the decimal 2 spaces to the left to convert that percent to a decimal. So you take the decimal that you obtain after you've converted the percent to a decimal, and you multiply by 500. So that means 500 times 0.21, we've got 105 particles of oxygen. Five hundred times 0.78. So that'd be 390 particles of nitrogen. And then finally 500 times 0.009 gives you 4.5 particles of argon. So of the 500 particles, 105 of them are oxygen, 390 of the 500 are nitrogen particles, and 4.5 out of the 500 particles are argon. Question 6, if you've got 0.045 parts per million nitrogen dioxide, what is that value in parts per billion? So we're going to be converting from part per million to part per billion. So what is the conversion factor that we need? A billion is 1 times 10 to the 9th. So 1 times 10 to the 9th parts per billion per every 1 times 10 to the 6th part per million. So that is the conversion factor that we'll need. So we take 0.045 parts per million, multiply it by the conversion factor. The parts per million cancel. So we do our math. 0.045 times 1 billion, 1 times 10 to the 9th, divided by 1 times 10 to the 6th. And you get 45 parts per billion. Question 7, convert 400 parts per million to a percent and convert it to parts per billion. And again, percent, the same thing as parts per hundred. So we've been working with that conversion factor a lot. So we'll need that conversion factor to convert the part per million to a percent, which is also called a part per hundred. And then we'll use this conversion factor here that we used in question 6 to convert the parts per million to parts per billion. So those are the 2 conversion factors that we'll use to solve this problem. 400 parts per million converted to parts per hundred, which is the same thing as a percent. (400) times 1 times 10 to the second divided by 1 times 10 to the sixth. And you get 4 times 10 to the negative 2 parts per hundred. And we just change that exponential to long form by putting a decimal at the end of the number, putting zeros in front, and moving the decimal 2 spaces to the left. You get 0.04 parts per hundred, or 0.04%. And then to convert 400 parts per million to parts per billion, we take 400, multiply it by 1 times 10 to the 9th power, and then divide that result by 1 times 10 to the 6th. And you get 4 times 10 to the 5th parts per billion. Question 8, nail polish remover was spilled in a room, and the room has a dimension of 6 meters by 5 meters by 3 meters. Measurements determined that 3,600 milligrams of acetone had evaporated. Calculate the acetone concentrations in micrograms per cubic meter. And so the dimensions of the room, we can calculate the volume of the room. And again, this is something that should be familiar. Volume is length times width times height. And those are the dimensions: length, width, height. So the volume of the room is 6 meters times 5 meters times 3 meters, which is 90. And you also should remember this. I'm not sure how long it's been since you've had a math class, but when you're multiplying and you have your units, those units, if those units have no exponent, then it's understood to be 1. And so therefore you take these 1s. And so when you're multiplying, you add the exponents. That's another math rule that should be familiar to you. So 1 plus 1 plus 1 is 3. So that's 90 meters cubed. And that's called a cubic meter. Meters cubed is also called a cubic meter. So we need to take this 3,600 milligrams and convert it to micrograms, and then divide by the volume of the room that we've just calculated in cubic meters. So we're going to calculate the concentration of acetone in micrograms per cubic meter. And so we know that for every 1 milligram, we go back to our metric conversions table that we should have noticed and seen in our textbook for chapter 1. And that same type of table is also in the math review packet that I posted on the news section of our eLearn homepage. So 1 milligram is 1 times 10 to the negative 3 grams. One microgram, and health professionals, they call it mcg, the microgram. But us chemists, we use the Greek letter mu to stand for micro. Either symbol is considered correct. In the healthcare field, they use mcg. So 1 microgram is equal to 1 times 10 to the negative 6 grams. So these are two equalities, and we should know by now that an equality is the same thing as a conversion factor. We can take the equality and we can convert it into a fraction, which will mean the same thing as the equality. So 1 milligram per every 1 times 10 to the negative 3 grams. And there's 1 microgram per every 1 times 10 to the negative 6 grams. So those are our two conversion factors. So first, we're going to have to convert milligrams to grams, and then we're going to convert grams to micrograms. So 3,600 milligrams and I like using my railroad tracks when I'm doing a long conversion. That's a 2-step or 3-step conversion. You can do it this way, or you can do it the way I've been doing it when I'm doing single conversions. It doesn't matter, it just depends on what you're comfortable with. So 1 milligram, I want to get rid of milligrams and I want to convert it to a gram. So my denominator of my fraction, which is a conversion factor, I'll need to put milligrams. I want grams, so grams go in the numerator. Remember, the unit you're trying to convert from will go into the denominator, which is the bottom part of the fraction in your conversion factor. The unit you're trying to convert to goes into the numerator, which is the top part of the fraction. So we got 1 times 10 to the negative 3 grams per every 1 milligram. So now milligrams cancel. And then this is a 2-step conversion. So now I need to convert the grams to micrograms because that's what the problem wants. They want micrograms per cubic meter. So for every 1 microgram, I want micrograms, so micrograms go in the numerator. There's 1 microgram per 1 times 10 to the negative 6 grams. So now my grams cancel. So 3,600 milligrams is how many micrograms? We take 3,600, we multiply by 1 times 10 to the negative 3. And then we divide by 1 times 10 to the negative 6. And that gives us 3.6 times 10 to the 6 micrograms. But we want micrograms per cubic meter. So we've got to divide this micrograms by our volume of the room, which we already calculated to be 90 cubic meters. So therefore, 3.6 times 10 to the 6 micrograms divided by 90 cubic meters kind of running out of space here. So we take our result, our 3.6 times 10 to the 6 micrograms, and divide it by 90. And that gives us 4 times 10 to the 4th and the units are micrograms per cubic meter. So that's the concentration of acetone in the room in units of micrograms per cubic meter. Question 9. Calculate the volume of air in liters that you might inhale and exhale in 1 hour. Assume that each breath has a volume of 0.45 liters. That's the conversion factor, 0.45 liters per breath. And you're breathing 10 times a minute. That's another conversion factor, 10 breaths per minute. And so you should have been able to read that problem and pick up on that this information that you're given in the problem are conversion factors. So it's very important to read the problem carefully and to be thinking critically at the same time. Everything is not going to be on a silver platter. You're going to have to read problems and you're going to have to extract information out of the problem. So you're going to have to use your critical thinking skills. So therefore, in 1 hour, how much air will you breathe? So we take 1 hour and we're going to multiply it by these 2 conversion factors. But we're going to need a third conversion factor because an hour is a unit of time, and then a minute is another unit of time. That's like an apple and an orange. I can't cancel out an hour with a minute. So I need to know the conversion factor to convert between hours and minutes, and we all know that. There are 60 minutes per every 1 hour. So there's a third conversion factor that we're going to need to use to solve this problem. So for every 1 hour, there are 60 minutes. So now the hours have canceled. And there are 10 breaths per minute. And now the minutes cancel. And there are 0.45 liters per breath. And now breath cancels. And now you're left with the unit that you want, and that's liter. So now just do the math. 1 times 60 times 10 times 0.45. And that gives you 2.7 times 10 to the second liters. So that's how much air you will breathe in 1 hour. So question 10 deals with chemical reactions. Read the following steps of how ozone, a secondary pollutant, is formed. Provide a balanced chemical reaction that explains each step. So for part A, nitrogen monoxide, NO, is produced. And so that means that nitrogen monoxide is the product. So again, you have to read the problem and extract that information from the reading of the problem using your critical thinking skills. And NO, nitrogen monoxide, is produced when nitrogen and oxygen are exposed to high heat. So nitrogen and oxygen are your reactants. They go on the left-hand side of the chemical reaction. NO is your product. It goes on the right-hand side. And in between the two, you put an arrow. That's how chemical reactions are written. You have an arrow that separates the reactants on the left-hand side from the products on the right-hand side. And then to balance this correctly, we needed a 2 in front of NO because there are 2 nitrogens on the left. So we need 2 nitrogens on the right. There are 2 oxygens on the left. So we need 2 oxygens on the right. This 2 coefficient is for the nitrogen and the oxygen. Part B, at high concentrations, nitrogen monoxide will directly react with oxygen to produce, put my arrow, nitrogen dioxide, NO2. And so, to balance this equation, we've got 1 nitrogen on each side of the equation, but we've got 1. Remember, if there's no subscript, it's understood to be 1. So we've got 1 plus 2, 3 oxygens on the left, but only 2 oxygens on the right. So what we'll do is put a 2 in front of the NO and a 2 in front of the NO2. So now we've got 2 nitrogens on each side, and we've got now 2 times 1 is 2, plus 2, 4 oxygens on the left, and 2 times 2, 4 oxygens on the right. So now that equation is perfectly balanced. So this is the ideal way that nitrogen dioxide is produced in the atmosphere. However, if you continue reading the question, you'll see that in the atmosphere, the production of nitrogen dioxide is more complex than what we could do in a general laboratory setting. So in the atmosphere, this reaction is more complex, meaning that there's more than one step needed to produce nitrogen dioxide from NO and O2. And so the problem says that one complex pathway to nitrogen dioxide requires the presence of volatile organic compounds. That's what this VOCs stand for. And you should have read about this in chapter 2. So this complex pathway involves VOCs and the little dot plus OH. That's a hydroxide free radical. OH is the symbol for the polyatomic anion hydroxide. And then having that little dot in front of it means that it's a radical compound. That's all you need to know about that right now. If you go on to take organic chemistry, then you'll learn more about radicals and how they play a role in many types of reactions. Another thing just to note about these free radicals is that they are very, very reactive. They react very fast. And so the complex reaction between a VOC and the radical produces some intermediate compound that we'll just call A. And then that intermediate compound will then react with the oxygen. And that will form a second intermediate that we'll call A prime with the little quote symbol. And then that second intermediate is going to react with the NO. And then finally you get NO2. So that's the more complex steps of reactions that take place. But what you'll have is the A intermediate that was produced in the first step, it gets consumed in the second step. And then the A prime intermediate that gets produced in the second step gets used up in the third step. And so in the end, you have your O2 and NO combining via these intermediates to get you your final product, NO2. In reaction C, energy from the sunlight is a catalyst. The sunlight is a catalyst for many reactions, including photosynthesis. And usually for chemical reactions, if there's a catalyst involved, you'll write the name of the catalyst on top of the arrow. So energy from the sunlight splits nitrogen dioxide. So NO is our, NO2, nitrogen dioxide, is our reactant. It splits nitrogen dioxide to oxygen and nitrogen monoxide. So oxygen and nitrogen monoxide are our products. So now we need to balance this equation. So again, we've got 3 oxygens on the right and 2 oxygens on the left. Notice that this reaction is the reverse of the reaction that we did in part B. So we'll put a 2 here, a 2 here, and now we have a balanced equation. And so the next section of the questions deals with balancing equations. So the thing you want to make sure is that you've got the same number of each type of atom on both sides of the arrow. So here we have PT, platinum. There's 1 on each side, but the fluorine, there's 2 on the left and 6 on the right. So in order to have 6 fluorines on the right, we need to put a 3 coefficient in front of F2. 3 times 2 is 6. And so we just put 1s in the other blanks, and now we've got a balanced equation. So B is the correct answer. Number 2, we need to balance this one. We notice we've got 2 aluminums on the right, but only 1 aluminum on the left, so we put a 2 here. Oxygens, We have 3 oxygens on the right, but only 2 oxygens on the left. So what's the least common multiple between 2 and 3? It's 6. So 2 times 3 is 6, so I need to put a 2 here. So now I've got 6 oxygens on the right. 3 times 2 is 6. So now I've got 6 oxygens on the left. Now I've got also 3 manganese, Mn, atoms on the left. So I need to put a 3 coefficient here in order to have 3 manganese atoms on the right. So my correct answer, 3, 2, look at my aluminums. Putting a 2 here gave me 4. 2 times 2, 4 aluminums on the right. So now I got to change this 2 to a 4. Now I've got 4 aluminums on the left. 2 times 2 equals 4 aluminums on the right. So 3, 4, 3, 2 is my correct answer. Letter D. Question 3 involves all combustion reactions. Combustion reactions normally involve a hydrocarbon compound reacting with oxygen, a hydrocarbon compound, meaning that it contains carbons and hydrogens, and the products are always CO2 and water. So balancing these, for combustion reactions, these are some rules of thumb. Balance the carbons first, then the hydrogens, and then last, balance the oxygens. And then a second rule of thumb, if there are an even number of carbon atoms in the formula of your hydrocarbon, then a fraction or decimal is needed to balance the oxygens. So the first one, letter A, CH4, only has 1 carbon. Remember again, if there's no subscript, then it's understood to be 1. So to balance this one, we need 1 carbon. We'll balance the carbons first, and they're already balanced. There's 1 carbon on the left, 1 carbon on the right. Next, let's balance the hydrogens. We've got 4 hydrogens on the left, but only 2 on the right. So we'll put a 2 coefficient there to give us 2 times 2 equals to 4 hydrogens on the right. And then finally, let's balance the oxygens. We've got 2 oxygens provided by the 2 water molecules. Each water molecule has 1 oxygen. So if you've got 2 water molecules, you've got 2 oxygens total. And you've got another 2 oxygens there with the carbon dioxide. So a total of 4 oxygens on the right, but only 2 oxygens on the left. So we put a 2 coefficient here. Now we have 2 times 2 equal to 4 oxygens on the left. So the carbons are balanced, the hydrogens are balanced, and the oxygens are balanced. We don't need to, but just for bookkeeping purposes, we'll put 1s in the blanks in front of the methane, CH4, and the carbon dioxide, CO2. So now our equation is balanced. Part B, C2H6. So this is a hydrocarbon that has an even number of carbons. So we know there's going to be a fraction needed here to balance the oxygens. So first, let's follow our rules. Let's balance the carbons first. We've got 2 carbons on the left, but only one carbon on the right. So we're going to put a 2 coefficient here in front of CO2. Now we've got 2 carbons on the right. Next, let's balance the hydrogens. We've got 6 hydrogens on the left, but only 2 hydrogens on the right. So to balance that, 3 times 2 is 6, so we put a 3 coefficient there. And now we have 6 hydrogens on the right. And then finally, let's balance the oxygens. We've got 3 times 1, which is 3 oxygens provided by these 3 water molecules. And then we've also got another 2 times 2, 4 oxygens provided by the CO2 molecules, and there's 2 of them. There are 2 oxygens per CO2 molecule. So if you've got 2 CO2 molecules, that's 4 oxygens. So 4 plus 3 is 7. I've got 7 total oxygens on the right, but I only have 2 oxygens on the left. So I put my fraction, 7 over 2, in front of the oxygen. 7 over 2 times 2 is 14 over 2, which is 7. So now I've got 7. Now I've got 7 oxygens on the left. And now my reaction is completely balanced. The next one is propane. C3H8 is propane. C2H6 is ethane. CH4 is methane. These are all hydrocarbons. They come from crude oil. And this is propane. If you have a gas grill, then you've got a propane tank connected to your gas grill. And so C3H8, we balance the carbons first. There are 3 carbons on the left. So therefore, we need to put a 3 coefficient in front of CO2 in order to have 3 carbons on the right. We've got 8 hydrogens on the left, but only 2 on the right. 4 times 2 is 8, so we need to put a 4 coefficient in front of the water. Now we take a look at the oxygens. We've got 4 times 1, which is 4 oxygens provided by the 4 water molecules. And we've got 6 oxygens provided by those 3 CO2 molecules. Each CO2 molecule having 2 oxygens. 2 times 3 is 6. So 6 plus 4 is 10. So I need to put a 5 here. 5 times 2 is 10. So now I've got 10 oxygens on the left as well. So now part C is completely balanced. The next one, C4H10, is butane. That's the type of hydrocarbon that's in cigarette lighters, the little the fireplace, little lighter, little wands that you use to light your fireplace or to light your grill. All of those things have butane fuel in them. And of course, butane is also a hydrocarbon that comes from crude oil. And so we've got 4 carbons on the left, so we need 4 carbons on the right. We've got 10 hydrogens on the left, but only 2 on the right, so 2 times 5 is 10. So we need to put a 5 in front of the water. Now we've got a total of 5 times 2, 10 hydrogens on the right. Last, we balance the oxygens. We notice butane has 4 carbons, so that's an even number of carbons, so we're going to need a fraction to balance this one, to balance the oxygens. So we count up the oxygens on the right. We've got 5 oxygens provided by the 5 water molecules. Each water molecule has 1 oxygen. So if you have 5 water molecules, you've got 5 oxygens. But also there's oxygens in the CO2 molecule. Each CO2 molecule has 2 oxygens. And if there are 4 of them, 2 times 4 is 8. So 8 plus 5 is 13. So we put 13 over 2 as our coefficient in front of the oxygen. And now our butane combustion reaction is balanced. And in part E, we still have butane, C4H10. But this time our product is carbon monoxide, CO, in water. Anytime carbon monoxide is one of the products of a combustion reaction instead of CO2, that's called an incomplete combustion reaction. That means that there's limited oxygen available. So like if you start your car in a closed garage and then you go back in your house and you end up getting a phone call to interrupt you, and you end up staying on that phone call for 30 minutes while you're letting your car run in an airtight closed garage. What's going to happen is eventually all the air in that airtight garage is going to get used up. The air contains the oxygen that's needed for combustion. So now you're in a limited oxygen environment, and the octane, which is another type of hydrocarbon, that's the major component that's in the gasoline in your car. So now the octane has very little oxygen to react with. And so now instead of CO2 and water coming out of the tailpipe of your car, now dangerous poison carbon monoxide is coming out of your tailpipe. And then if you let that car run too long in that garage in that manner, carbon monoxide is going to fill your garage. And that could be very dangerous. So always start your car in an open garage. Make sure you open that garage door before starting your car. And so let's balance this incomplete combustion reaction in which carbon monoxide is a product instead of CO2. We follow the same rules. We'll balance the carbons first. So we got 4 on the left. We'll need 4 on the right. Next, we balance the hydrogens. We've got 10 on the left, so we need 10 on the right by putting a 5 here. Now last, let's balance the oxygens. We've got 4 plus 5, which is 9 oxygens on the right, so we need 9 oxygens on the left, so we put the fraction 9/2. So we can see that these same two reactions, D and E, both having butane, but for the incomplete combustion reaction, you've got less oxygen available than in the complete combustion of butane. So D represents the complete combustion of butane. E represents the incomplete combustion of butane, where there's less oxygen available. 9/2 is smaller, of course, than 13/2. Question 4, to burn 1 molecule of C4H10, we're dealing with our butane again, to form CO2 and water, which is complete combustion, because CO2 is our product and not carbon monoxide. How many molecules of oxygen are required? So we can go right back to the complete combustion reaction that we just did. We've got 1 molecule of butane. We're forming CO2 and water. How many molecules of oxygen are required? 13/2. So we already have our answer right there. And that brings us to the end of the Chapter 2 practice work. I hope you found that to be helpful. If you have any remaining questions on Chapter 2, please just send me an email and I'll be happy to answer your question.